Welcome back to SMJP 2123 Thermodynamics. So continuation from the last lesson on pure substance, we are going to dive into applying our knowledge on using the properties tables on the construction of PV and TV diagrams. So last time we went through what are PV and TV diagrams, how do they look like, what are the critical points, critical pressure, critical temperature. We went through the vapor dome where we learned about the saturation liquid line, saturated vapor line, so all those knowledge we will use serve as a background for our problem examples here. We know that P and T are independent properties or intensive properties. V also is an intensive properties, which is the specific volume. P is for pressure, T is for temperature, and V is for specific volume. And to know what are these processes properties, we have to know at least two of these intensive properties. But let me just back up a second and list down what are the processes that are involved in this example. Now we have this process which is operating at 3 megapascals of pressure and 350 degrees Celsius of temperature. This is our first process, right? So we have state 1 here. Okay, the fluid is at state 1. And then the fluid, which is in this case the steam, right, is cooled at constant volume until its temperature reaches 195 degrees Celsius. This is the second state. So this is state 2. Then it is compressed at constant temperature until its pressure becomes 2 megapascals. So this is state 3. So we know that there are 3 states altogether of the fluid under question, which is water, or in this case steam. And then we have no further processes going on, right? So we know that there are 3 states of the fluid. So what I'm going to do now is to sketch my PV diagram and my TV diagram, but I'm not going to complete the sketch until I finish the exercise. So just a preliminary sketch or an initial sketch of the PV diagram and also the TV diagram. Let me just put the axis first, right? So this is for PV diagram, right? Let's hope this is big enough. Pressure is in megapascals and specific volume is in meter cube per kilogram. Let me do the same for temperature versus specific volume. T, okay, in the y-axis, and again V in the x-axis, right? So that's gonna be meter cubes per kilogram. This is temperature in degrees Celsius. All right, we are gonna revisit these PV and TV diagrams quite a couple of times. Let me just put the basic curve here. For PV diagram, we have something like that, quite skewed, all right? And for a TV diagram, we have something like a bell-shaped curve. Let me just adjust this so that I have enough space to draw my isotherm lines. So something like that. And I'm gonna do the same for the one at the bottom. All right, that's good enough. All right, good. So we know that the critical pressure is at 22.04 megapascals, and the critical temperature is at 374.14 degrees Celsius. So you know that you would not exceed this temperature for the given question, right? Everything is below the critical point. For example, the temperature here is 350 degrees Celsius. So it's just below the critical temperature. So everything is still within the vapor dome, all right? I like to separate, the states and the requirements for each state, right? So for example, state 1, we have pressure is 3 megapascals, temperature is 350 degrees Celsius. What else do we know? We have the mass is 3 kilograms, right? And then state 2, we know from state 2 that the steam is cooled at constant volume until its temperature reaches 195. So we have cooling, V1 is equals to V2, right? Constant volume. Cooling at constant volume. Now here, temperature is 195. Do we know the pressure? We do not know. And the question further asks for the quality and the pressure at state 2. So there's another one variable we do not know, which is quality, right? Quality X. Now, state 3, we have the fluid being further compressed at constant temperature until pressure becomes 2 megapascals. So this one is a constant temperature. So T3 equals to T2. And then we know the pressure is 2 megapascals, right? 2 megapascals. Question further asks that what is the cylinder volume at state 3? So we do not know the volume also. Now, let's start by slowly going through state 1. We have pressure of 3 megapascals and temperature of 350 degrees Celsius. First check is, what is the phase? What is the phase? Okay, is it in a superheated vapor over here, or is it in a condensed liquid over here, or is it a mixture of saturated liquid and saturated vapor inside this vapor dome? So we have to know that first by checking our properties table. Let's look at the given information. First here is the pressure is 3 megapascals, right? Pressure is 3 megapascals. We refer to table A5 for the variation in pressure. So we see 3 megapascals in table A5, right? So the pressure here is in kilopascals, right? It's in kilopascals. We want to go with 3000 kilopascals. That will turn out to be 3 megapascals. 3000 kilopascal, right? Now we see that the saturation temperature corresponding to that pressure is 233.85 degrees Celsius. Okay, so let's check our temperature. Is it more than that? Yes, it is more than that. 350 degrees Celsius is way higher than the saturation temperature, meaning it's the temperature higher than the temperature required to turn that water into steam. So basically our T here is greater than the T sat, okay, which is 350 degrees Celsius, greater than 233.85, right? So we know that if the saturation temperature is lower and we have a temperature higher than that, that means our liquid or our steam is in a superheated vapor region. Alright, so I'm gonna declare this as a superheated vapor. Right, so this one I checked from table A5. for superheated vapor, the property table is A6, and so we are going to visit that table. A6, our pressure is 3 megapascals, so let's go down to 3 megapascals. Okay, here we go, 3 megapascals, and then we have a temperature of 350 degrees Celsius. So we are looking at this row here, 350 degrees Celsius, and we know that our V is in the first column here in this section. So the first column is, let me double check, yes, it is V, our specific volume, and that's going to be 0.09056. So our specific volume is 0.09056 meter cube per kilogram. Okay, so V1 is this value. Let me just box that, and let's just put that on the diagram here. Okay, so somewhere here, okay, 0.09056, we have our superheated vapor region. Okay, so this is superheated vapor region. Okay, so that's all we can gather from state 1 for now, and we go to state 2, right? We know state 2 V1 is equals to V2, right? V1 is equals to V2. Okay, cooling at constant volume. We want to find what is the pressure at state 2. But first, let's check what is the phase. Okay, so we are done with state 1. Okay, now it's state 2. Okay, we have temperature of 195. So we know 195, the temperature base table is A4. So I'm gonna go with table A4. 195 degrees Celsius. And so I know that my VF and VG are in this section of the table, in the blue box there. So I'm just gonna write it down. VF is 0.001149. VF is 0.001149 meter cube per kilogram, and VG is 0.1414089. Okay, 0.14089 meter cube per kilogram. Why do I check for my VF and VG? Because I know my V2 is equals to V1, that is 0.09056. 0.09056 meter cube per kilogram. So if you notice, my V2, right, 0.09, is between VF and VG. That is, it's between the saturated liquid and the saturated gas. That means when my V is between VF and VG, then my fluid is in a vapor mixture. Okay? So I know that if my liquid is in a saturated liquid vapor mixture, then I must have this quantity called quality, right? Quality. My fluid is somewhere inside here, okay? Somewhere inside this vapor dome. So let me just put the number there, 0.09056, 0.09056, which is already there, right? So meaning by constant volume cooling process, that means it goes from state 1, let me just draw my state 1 at the superheated vapor earlier, to state 2, going down like that, right? So it's not going to go sideways. It's going to have a constant volume or no change in volume, whereby you go only in the downward direction. And you know, it's inside the vapor dome, so it's not going to stop here. Yeah, so it's going to stop somewhere here, right? So that's going to be your state 2, right? So that quality there is representative of a state inside the dome, right? So x here is let's say 0.5, maybe over here x equals 0.1, here maybe x equals 0.9, right? So you know, with the shift from the left to the right of the dome, you will have a bigger number closer to 1. So that's how the quality works, right? It assesses how much vapor content or percentage of vapor is there in the liquid vapor mixture. We are asked about the quality, okay, at state 2, x, and also the pressure. Let's start off with the quality first, because we know quality is a calculation that involves V sub f and V sub g, right? So quality is equals, if we recall our formula, that's going to be V, which is the specific volume of that state, minus specific volume of the liquid, over Vg minus Vf, which is the specific volume of the vapor minus the specific volume of the liquid. Now we have all these values, right? We have V2, which is this guy, 0.09056, minus Vf, which is this guy, 0.001149. Okay. V sub g is 0.14089, and V sub f is again 0.001149. And if we punch these numbers into our calculator, we will get the value of 0.64. Let me just write that down. X at state 2 is 0.64, right? Meaning approximately 64% of vapor inside the liquid vapor mixture. Now the pressure you can obtain from table A4 based on the temperature of 195 degrees, right? So we check for table A4, 195. So why do we check table A4, not table A6, for example? Yeah, anything in table A4 and A5 we can use for the state inside the vapor dome, or on the saturated liquid line or saturated vapor line. Anything outside that, towards the superheated vapor, we will use table A6, right, which is the superheated water category, right? And anything towards the left side of the vapor dome is considered a compressed liquid, with the respective table being table A7. So when we have, for example here, okay, it's inside the vapor dome, so we are going to put our focus on either table A4 or A5, right? Depending on the question. If temperature is given, then we look at table A4. If pressure is given, A5, right? So now 195 degrees Celsius in table A4, temperature based. We know that from the table at 195, the pressure is 1398.8 kilopascals. So pressure equals 1398.8 kilopascals, or 1.3988 megapascals. Let me just box that in red. So now at state 2, we actually have a pressure of 1.3988 megapascal, which is somewhere here, right? So here is 1.3988 megapascals. Just now it was here 3 megapascals, right? So this is not drawn to scale, so everything is in a relative fashion. So bigger means up there, smaller means down here. We'll get to the TV diagram later when we have finished our PV diagram, right? Now we have answered question 2. Moving to state 3. Okay, let me complete this PV diagram by drawing the isotherms, right? I'm going to draw the isotherms using a different color now. Let me use blue one. So let me start with this line first. And then the way we draw isotherms in a PV diagram is that it always goes from the top at the left side towards the bottom on the right side. And we have state 2, something like this. And then like that. And then that. Okay. So that completes the PV diagram, right? The PV diagram will have an axis, y and x axis, and then the vapor dome in the red, and then the isotherms in blue. So at state 1, the temperature is 350, right? T is 350 degrees Celsius. At state 2, T is 195 degrees Celsius. So now we go to state 3, right? At state 3, we have a compression of the fluid at constant temperature until pressure becomes 2 megapascals. Now let's assess what phase is this, right? Let's check the pressure. Okay, the given value here is pressure, right? So 2 megapascals, we compare that with the previous state, which is 1.3988. Okay, so 2 versus 1.3988, 2 is bigger, right? So this is for state 3. P3 is larger than P2, right? So at state 3, the process that happens is the compression at constant temperature. When you start to compress from highly vaporized state, like a vapor state, you compress, right? It will become a liquid. It starts to become liquid. So when you see at a constant temperature, the compression is happening at constant temperature, you are actually going along this isotherm. This isotherm means the temperature is constant, and then you are going this way, right? You are going somewhere here, all right? I don't know where it will stop, but you know, it's going this way, okay? We will know the stopping point when we find out what the phase is, right? So now, how do we actually know what is the phase of state 3? Okay, so let's compare what we have at hand, which is 2 megapascals of temperature, right? And we compare with the previous state. Here, what was the pressure? The pressure was 1.3988 megapascals, right? But now it has gone to 2 megapascals. So it has actually traveled here along this isotherm, okay, where the temperature is constant, and here also the temperature is still constant, right? So it stops somewhere there at 2 megapascals, okay, 2, okay. So it's a little bit different from your XY plots, yeah, your normal XY plots, where you know, once you have reached a constant value, you know, it will just drag to the y-axis. But here, not really. You have to follow the isotherm, right? This light blue line, okay? You have to follow this isotherm all the way, you know, to 2 like this. Not, you know, follow the isotherm all the way till the y-axis. No, you have to follow along the isotherm until you reach, you know, a value that is larger than 1.398 but lesser than 3, which is 2 as given by the question. So now we can define the third state, which is right here. Okay, I'm going to put a small arrow there to indicate the process. Now we have the complete process being drawn on the PV diagram, right? one at the super vapor state, two in the under the vapor dome, and number three in the compressed liquid state. All right. Now, what is the table that you are going to refer to for compressed liquid phase? Your first thought should be by now is table A7. All right, table A7 specifies all the properties for compressed liquid. So if we look at table A7 and we check our pressure and temperature, it is out of bound, right? Because we have 2 megapascals here, all right? But we do not have 2 megapascals in the properties table in A7. Okay, 2 megapascals is not going to get us anywhere from this table. For that, we will use table A4. Okay, usually when we look at compressed liquid, the difference between a compressed liquid and the saturated state is very, very little. Okay, and so we can approximate a compressed liquid with a V sub F. V sub F is the saturated fluid or the saturated liquid. Okay, so we go to table A4. Yeah? We do not go to table A5 because properties of the fluid are, especially for enthalpy, sensitive towards temperature. Okay, so we are going to use temperature based table for compressed liquid. In this case, A4. Yeah, A4. So coming back to A4 at 195, you are going to look for VF. Yeah, V sub F. So 195 V sub F is 0.001149. Okay, I think we saw that earlier. Yeah, 0.001149. All right, so in reality, this may have been drawn not so much to scale, but really this point and this point is very close. Yeah, they are very close, so we can approximate. Okay, approximate. So here the specific volume at state 3 is approximate to V sub F, right? Approximate to the V sub F, which is 0.001149 meter cube per kilogram. We know the mass, which is given in the question. Okay, so volume equals V state 3 times the mass, 0.001149 times 3 kilograms, right? If I'm not mistaken, 3 kilogram of steam. Okay, now that will turn out to be 0.003447 meters cubed. Okay, so now you have just drawn PV diagram, right? State 1, 2, and 3. All right. What about the TV diagram? The TV diagram is something similar, except that you have your isobar lines going up, right? From the left, it's going to go up. Let's start with 350 degrees Celsius, which is right below the critical point. Let's start with the 350, right? 350 line. So this is 350. But this one is in superheated vapor region. So it's somewhere here. Okay. And then we look at this PV diagram and we try to map to the TV diagram, right? So state 1 is in the superheated vapor region. So we say that state 1 is here. Let me draw with a different pen. This is state 1. Okay. So state 1 is at 350 degrees Celsius. And because it is in a superheated vapor state, we know that it's not going to have the saturated temperature of 350, but something lower than that, right? Something lower than that. So like that, and then like that, and then like that. Okay. So this is how a TV diagram looks like. The isobar will go up from left to right. And then at state 2, it goes down at a constant volume, right? So cool at a constant volume until temperature reaches 195. Okay. So let's put another isobar. Okay. So that will be a constant volume cooling process. So it's going to go vertical like that. And then our state 2 has a quality, meaning it is extended to the interior side of the vapor dome. So like that, okay, until it reaches this temperature of 195, okay, 195 degrees Celsius. Let me just back up a second. So at state 1, the pressure was 3 megapascals. So this is isobar of 3 megapascal. This is an isobar of, what is the pressure at state 2? It is 1.3988 megapascals. So this is an isobar of 1.3988 megapascals, right? And so now we have state 2 at this point. And then at state 3, we have constant temperature, and the pressure is at 2 megapascals. Okay, you know that 2 megapascals is in between 3 megapascals and 1.3988 megapascals. So you can guess that there is another isobar in between these two, right? That goes like that and like that, which represents 2 megapascals of pressure, of constant pressure, sorry. So that pressure is 2 megapascals, right? At state 3. And so now your fluid goes from state 2 to state 3 at constant temperature until it reaches 2 megapascal, which is that point, right? That point there. So let me just draw that with a red pen. Okay, that is state 3. Okay, notice that the state 3 is going along this 2 megapascal line. Okay, 2 megapascal isobar. Okay, so it makes sense, right? So this is what our TV diagram will look like. Okay, from state 1 at the superheated vapor to state 2 with the quality, with the mixture, and to state 3 in a compressed liquid state. Okay, you can find out what is the temperature at 3 megapascals. Okay, just look up at the A5 table. Okay, so that's how you draw a PV diagram and a TV diagram using properties table as your guide. Okay, hopefully you get something good out of it. See you next time.